Okay, so welcome everyone. So welcome to the IMSC 60 Colloquium series, and it's a great pleasure for us that we have Professor Diptimoy Ghosh with us. So Diptimoy did his PhD from TIFR, working on B physics and also many other topics in particle physics. And his thesis work was awarded the Rahul Basu Best Thesis Award for the year 2012. Which was the best thesis in theoretical high energy physics during the year 2010 to 12. Later he went to do his postdoctoral research in University of Rome, La Sapienza, where the last year's Nobel laureate Giorgio Parisi belongs to the same university. And then after that he was at Weizmann Institute and later briefly at ICTP. And then he joined as a faculty member at IISER Pune. So Diptimoy has a wide range of interest. He has worked on several interesting problems in B physics, neutrinos, and dark matter. And many of his works are very highly cited. And I guess it will serve you as an inspiration that even at this very young age, he has very highly cited papers, some of which are more than 200 citations. So without much more, I request Diptimoy to kindly give his colloquium. Thank you for coming.
Hello, can you hear me well? Okay, so it's really an honor for me to be part of the 60th foundation year of IMSC. One of the best research institutes in India, and the main theme of my talk today is going to be spatial relativity and in particular relativistic causality. And if you know about, or some of you might know that the founding father of this institute, Professor Alladi Ramakrishnan, was also fascinated by spatial relativity and spent quite some time understanding it, and in fact he even contributed to this subject. So I'm glad that I'll be talking to you about a topic which is mainly developed around the idea of spatial relativity. And I really thank you for giving me the opportunity to be part of this celebration. Now, as once one of my teachers told me that colloquia are most of the time useless because for non-experts they're usually not very comprehensible, and for experts they're usually boring and unexciting. But I'd to not like to happen that here, and since the number here is not so large, at least by the IISER standard, where we see hundreds of people in colloquia, you can always ask me questions, stop me at any point if you have any questions, clarifications, or criticisms. Let me also just tell you at the beginning that I'm most probably be not adding anything to the subject and to what is already known before. So it's only exposition, at least mostly exposition, except maybe towards the end of my talk where I'll mention some of the new results which we have obtained. Okay, so the idea of my talk is to understand what the boundaries of quantum field theories are. So let me explain what I mean by boundaries of quantum field theories. You'll see many examples, but first I hope you all know that quantum field theory has served as a very general framework to study physics in diverse areas, for example, in particle physics, in cosmology, and also in condensed matter physics. So it's very important that we try to understand the space of consistent quantum field theories before we try to experimentally either verify or falsify them. So, and that's what I mean by boundaries of quantum field theories. So by boundaries, I mean the boundary of consistent quantum field theories. Now, once we write down a quantum field theory based on some principles, we can ask the following question. And the question is, what is the space of low energy effective field theories? By quantum field theory, I always mean a low energy effective field theory that admit UV completion either through string theory, quantum gravity, or within a low range invariant field theory alone. Now, since there are possibly some string theorists here in the audience, the space of quantum field theories which you get, the consistent quantum field theories which you get when you try to couple it to quantum gravity is often called the landscape as opposed to the space which is inconsistent, which is called the swampland, but that is not what I'm going to talk about in this talk. So here I'm interested in the consistency of quantum field theory within the framework of quantum field theory itself. So and I'm more interested to at least start with to understand this question, because here you can ask well-defined questions and you can answer these questions quite rigorously, as opposed to the case where you try to couple quantum field theory to gravity, where most of our understanding are at the level of conjectures and not rigorous proofs. And here I have a cartoon. You see that of the space of field theories, and the dashed circle shows the space of consistent field theories, and as we can expect, the standard model will be 1, but in general we would like to understand the space of all consistent quantum field theories. So that is the broad question we want to ask. But before we get into the details, let me first spend maybe 10 to 15 minutes try to understand why we are interested in effective field theories. So the very broad idea of effective field theory is the following, and not only effective field theory, just effective theories is the following, that one can make quantitative predictions of observables or observable phenomena without knowing everything. A slightly more technical version of the statement is that the dynamics at long distance does not depend on the details of what happens at short distances. The same idea often goes by various names, separation of scales, decoupling of heavy physics, and so on. But the basic idea is exactly this, that in order to understand, for example, physics of a chalk, if I just hurl it upwards, I don't really have to understand atomic physics, molecular physics, or even quantum mechanics, to a great extent. In fact, this is exactly the reason why Newton did not need quantum gravity for projectile motion. In fact, Newton did not even have to learn about general relativity or discover general relativity to describe projectile motion, or did not have to understand how the atoms or molecules inside an apple interact to understand projectile motion. This statement might sound obvious and silly, but you'll see that this is really at the heart of the fact that we can do science and we can do physics, because otherwise if we had to learn about every details of subatomic physics to understand physics at long distances, then I think we had no hope of doing quantitative physics at all. Now, when I say quantitative physics, I don't mean that you know the result exactly. I only mean that you know the result approximately, and this approximation can be improved in a systematic way. And this is always the case because experimental observations or experimental or measurements always have accuracies, and we never want to know the exact answer. We always want to calculate the answer to a level which is satisfactory given the experimental accuracy. Okay. So now a slightly more involved example, which you have all learned in undergrad physics. This is the example of multipole expansion. Now in multipole expansion, you know that the field far away looks just like a point charge. This is another example of effective theory, and in fact it's an example of effective field theory, also a classical field theory, because classical, I mean, this is an example from classical electromagnetism. In a slightly more quantitative way, you know that you can write the potential in an expansion of a small parameter A by R, where A is the typical spacing between charges and R is the distance, is the long distance scale in this problem, and R is the distance where you are trying to measure the potential from the charge distribution. Here, as I already mentioned, R is the long distance of the infrared scale, and A is the short distance of the ultraviolet scale. So the expansion here is in terms of the quantity delta, which is A by R, and in momentum space this is the same quantity 1 by R by 1 by A, and 1 by R you can call it as the momentum P, and 1 by A you can call as the cutoff, the energy cutoff of your theory. So this is the same expansion in P by lambda, which you are all familiar with from quantum field theory. Now let's talk about a different example of a hydrogen atom. Now in hydrogen atom, you know that once you solve the Schrodinger equation, which has parameters mass of proton, mass of electron, and alpha electromagnetism, then you can explain to a very good accuracy a lot of spectral transitions and so on. Now you might ask that, that why in order to understand hydrogen atom problem you don't need to know what a proton is made of. Because indeed proton, as you know, proton is made of various quarks. In fact, there are many quarks. There are also quarks which are extremely heavy compared to protons. So you can ask, without knowing how proton is made of, their constituents and so on, how can I even hope to understand the hydrogen atom problem? Now you can do that because you can measure the mass of proton, mass of electron, and alpha electromagnetism from low energy experiments, and from measuring them from low energy experiments you can make predictions at low energies. However, if you do not fix alpha at low energies, but if you fix alpha, let's say at very high energy, then for example, at energy much more than the top mass, and that's what I call alpha mu h, where this is the high energy scale, then through RG equation the alpha at low energy will be related to alpha at high energies, and this relation will depend on the top quark mass. Now you see that if you wanted to explain the hydrogen atom problem in terms of 3 parameters just, where MP and ME are the 2 parameters, and the third parameter is value of electromagnetic coupling constant at very high energy, you fix that, then you'd be unsuccessful, and you'd need to know the value of the top quark mass to actually explain what hydrogen atom does, because the value of alpha at low energies is dependent on the value of top quark mass. So naively you would think that you are always sensitive to physics at small distances or UV physics. However, you see that the whole point here is that you can explain the hydrogen atom problem in terms of parameters measured at low energies, not parameters which are fixed at very high energies. And this is the sense why you have decoupling, or you have a case where you don't need to know the details of high energy physics to at least explain results to a given accuracy. And in fact, this is very important, because imagine the case where the engineers who built the Anna flyover had to know about the top quark mass in order to know the density of steel, and that is important for building the bridge, because if you see carefully and if you fix the strong coupling constant at high energies, you will see that the top quark mass is the proton mass is very sensitive to top quark mass. In fact, proton mass goes as top quark mass to the power some positive number. If you fix alpha s at high energies and not measure it at low energy experiments, and then once the proton mass is sensitive to top quark mass, the density of steel, which relies on proton mass, will also depend on the top quark mass. So when we say that we can do IR physics, we can do infrared physics without knowing about UV physics, we always mean that we measure quantities or parameters of my theory from low energy experiments, and only when we do that we actually lose sensitivity to heavy physics or UV physics, and which is extremely important for us to explain the nature around us. Okay, so does that mean that we don't care at all about short distance physics? We can just do IR physics without even worrying or thinking about what could be the physics at short distances? The answer is no, because for example, the chiral Lagrangian, the chiral Lagrangian of pions is CP and CP invariant because the QCD, which is the UV physics of chiral Lagrangian, by construction actually is CP invariant. So from the low energy point of view, you might think that this is this is just as a fact of nature without any prior explanation, but you only have an explanation when you know that the UV physics or the UV physics is QCD, or the chiral Lagrangian comes from a more UV complete theory, which is QCD. In fact, there's a more interesting example which all of you know about, is the case of non-relativistic quantum mechanics and Pauli exclusion principle. Now, Pauli exclusion principle was a principle which did not come from any theoretical understanding. It just came. It was discovered to explain some experimental observations, and mostly some nature of some of the chemical reactions, and there was no understanding of why this was true. In fact, this was described as one of the grand mysteries in the world pre-relativistic time in the 1986 Dirac Memorial Lecture by Feynman, which you can even watch on YouTube. However, we understood why Pauli exclusion principle is true in more general words, why spin statistics is true, when we understood that that the UV physics is actually a low-range invariant theory, and in particular is a low-range invariant quantum theory, which is the quantum electrodynamics. So it's not that we we don't care or don't worry about the UV physics. We do and we should, because some of the observations which might look ad hoc and puzzling from the low energy point of view might have an explanation and a deeper understanding when we think about UV physics, and when we know which particular UV physics my low energy theory is coming from. Now, with that introduction to effective theories, let's go to effective field theory, which is parameterized by some operators and their coefficients, where the operators are completely determined by symmetries. Let's take an example. And let's take this example, and very old example of Maxwell's theory, and let's try to explain or understand whether photon scatters off another photon. Now, in Maxwell's theory, which is just h square, you know that this is a completely non-interacting theory. Here, there will be no scattering of two photon going to two photon. I'm talking about photon scattering at energies much below the electron mass. In fact, this was discussed in 1930s, even before quantum electrodynamics was formulated. So what you do, you write additional terms based on symmetries. What are the symmetries here? The symmetries are Lorentz invariance and gauge invariance. So you can write down these two additional terms, f square square and f tilde square. The dimension 8 terms, you might guess that they will be suppressed by some electron mass to the power 4. That's not so important, but since we know today that indeed this is true, because the next heavy scale is electron mass, I'll normalize the coefficient of this operator by alpha square plus me to the power 4. This is just a normalization. And then we have coefficients C1 and C2. Now, once we write down these terms, you see f has del of A, so these terms give you a vertex among 4 photons. So you have a diagram like this, and you will have photon to photon scattering. Now, of course, today we know that this diagram is generated from a loop of electron. And in fact, you can even calculate to leading order in perturbation theory that C1 and C2 are two numbers, 1 by 90 and 7 by 360. But if you did not know what the UV completion is, if you did not know about electron, below the energy of the mass of electron, the C1 and C2 are completely arbitrary parameters. So let's assume that they are arbitrary parameters, and let's do an exercise.
So this second term actually violates CP, so that is very much suppressed.
No, second term actually does not, because FF tilde is odd under CP, however this is square. So that's why it's even under CP. Okay. So now let's do this exercise. Let's try to compute the amplitude for photon going to photon. We'll just compute this by dimensional analysis. You see, the vertex has 4 derivatives because it's f square and f has 1 derivative. So that's why you can you know that there will be factors of energy coming from each derivative. So that's why there's omega to the power 4. In cross section, you will have amplitude square times phase space factor, amplitude square. And then just by dimensional analysis, you can fix that the phase space factor must have 1 by omega square. 1 by 16 pi is not so important, and you can compute also the phase space, and you'll figure out that it's 1 by omega square. And but just you can fix this by dimensional analysis because sigma has mass dimension 2. So sigma goes as frequency to the power 6. Just this you can just figure out by dimensional analysis. Now let's see what you get if you did not take gauge invariance very seriously. If you did not take gauge invariance very seriously, you would not write down the more complicated operators which I wrote down in the last slide. You will write down a simpler operator which is just mu square. This will also give you 4 photon vortex and hence will give rise to photon going to photon scattering. You do the same dimensional analysis and you find out that the omega dependence of sigma coming from this term is just 1 by omega square. So the sigma correct, which is the one goes as omega to the power 6, by the sigma incorrect, if you compute this for omega of order 1 electron volt, I am considering 1 electron volt because this effective theory is supposed to be valid much below electron mass, that's why I am considering 1 electron volt, and this ratio is 10 to the power minus 6. You see, this is a big surprise, this is a huge number, and you see that how important gauge invariance is. If we did not take gauge invariance seriously, and if we just thought that yeah, Maxwell wrote down Maxwell's equation, it follows from f square, so I don't know about gauge invariance, then I just write down a term without worrying about gauge invariance, then you would make a mistake which is a factor 10 to the power minus 46. So this tells us that symmetries and understanding the symmetries of the theory or even the UV theory can be extremely important even for practical reasons, because this is a scattering which people really wanted to understand. This is simple photon going to photon scattering, and you will see that you would go wrong by a factor of 10 to the power minus 46 if you did not know about gauge invariance. Okay, so I hope I have convinced you that symmetries, and I have given you two very powerful examples of symmetries, Lorentz invariance and gauge invariance, and I have told you how they can be very important to understand some apparently puzzling phenomena at low energies, because at low energies if we did not worry about gauge invariance, we would get a wrong answer by factor of 10 to the power minus 46, then we'll start worrying about it, will get puzzled and we will not understand why the experimental number is so different from what we actually calculate. In the same way, if we did not know about Lorentz invariance, we would just be puzzled about Pauli exclusion, and at some point we'll just think that this is just some fact about nature without any more deeper understanding. But however, both of these could be understood if once we realize that the nature secretly is Lorentz invariant, and also in the electromagnetism, in the photon scattering case, that you have to always respect gauge invariance. But now for the rest of the talk I'll be even more ambitious. And
there, in the photon example, not only gauge invariance but also CP symmetries.
No, so in the photon example you couldn't write anything else. See, these are the only two possibilities for the photon case, and here you couldn't write anything else. You could try to write down epsilon A, but that will vanish because this is the same A, and there's only one species, so you couldn't write anything else. So that's why I said that it's not that in QCD CP conservation is imposed on QCD. It just follows from gauge invariance. I mean, you just can't write down any term which is CP violating, except the Weizhoumin or the theta term, which anyway does not play any role for local physics. So I'm ignoring the theta term of QCD. Okay, so now I'll be more ambitious in the following sense. So now I have told you that I have an effective theory Lagrangian where the operators, so now I accept that I have to be consistent with the symmetries, So I'll be consistent with Lorentz invariance, I'll be consistent with gauge invariance. So I'll write down operators which are Lorentz invariant and gauge invariant. I'll not write down operators which violate these symmetries. And then I have coefficients, but you see nothing can tell me what these coefficients are, because the coefficients they're not determined by the symmetries. When the operator is symmetries, the coefficient is completely unknown. So in here also this was the case. You see that the gauge invariance told me that you can't write mu square, you have to write f square and square, but of course I did not know anything about the coefficients C1 and C2, because that's not determined by symmetries. But now I want to go beyond. I want to say that I want to ask whether we can get some idea about the coefficients, C5, 6 on this slide, independent of the UV completion. And why independent of the UV completion? Because it's true that some specific UV completion will generate some values of the coefficients. I already told you that QED generates some specific numbers for C1 and C2 in the Euler-Heisenberg example. But if we don't know the UV completion, then I won't know about these numbers. And since I'm a low energy physicist, I'm an effective field theorist, I want to understand whether there are some consistency criteria on C5, 6 based on or independent of the specific UV completion. Then that would be extremely powerful, because that would not that must be satisfied independent of how I UV complete the theory. So that is the question I'm asking. Okay. Now now it turns out that the answer to this question is, so naively the answer to this question will be a strict no, because symmetries will not tell us about coefficients. I've already assumed that it's Lorentz invariant, the operators are Lorentz invariant, so the Lagrangian is Lorentz invariant. I already assumed that it's gauge invariant, so the Lagrangian is gauge invariant. What more can we do? So naive answer to this question is a strict no. However, it turns out that it's not so hopeless. One can learn something about the coefficient beyond what one can do based on just symmetries. I mean symmetries of the operators. So let me read out these two statements first. So the first statement is the following. So it turns out that even in this with this Lorentz invariant, gauge invariant, local Lagrangian, small fluctuations about generic background, I'll explain these words in detail, can propagate superluminally. So that means with velocities faster than light, making it impossible to define a Lorentz invariant time ordering of events. As you know that if there is a propagation speed more than 1 in units of c equal to 1, then you can always go to another frame where the ordering of events will change. So it turns out that even in this Lorentz invariant Lagrangian theory, you can have a situation where propagation of fluctuations about some non-trivial backgrounds can be superluminal, and that you can use to put constraint on it. You will see some simple examples of this. And then the second statement is that not all Lorentz invariant and gauge invariant theories are compatible with microscopic S-matrix, satisfies the usual analyticity conditions in unitarity. I'll also discuss this in more detail, leading to some low energy forward scattering amplitude to be positive. This is called S-matrix positivity. So let's see how this works and can give us constraints on the coefficients. So first let's consider this very simple theory of a scalar field which has a shift symmetry. So this is a very simple Lagrangian. So you have a kinetic term del pi square and then del pi to the power 4. This is the leading higher derivative term. and the coefficient is defined as k by lambda to the power 4. Now, as far as an effective field theorist is concerned, the coefficient, sorry, this C3 is k, so I think, so the coefficient k is completely arbitrary because it's symmetric, which I have assumed, then of course it's Lorentz invariant. However, let's consider a non-trivial background such that del mu of pi naught is the value of pi in the background, to be c mu, where c mu, just for simplicity I am taking it to be constant. But del mu of pi is not 0. If it was 0, it would be a trivial background of scalars, this constant, but this is not constant, this is a non-trivial background. And then ask what the speed of fluctuation is about this non-trivial background. Now, this is exactly, I mean, this kind of thing you can even set up in experiments. So for example, if you have a lab, if you have electromagnetic field, you can turn on a non-trivial background for electromagnetic field, let's say some constant electric field or something, and then you can ask if you fluctuate it slightly from the background, then what the propagation speed of small fluctuation is about that non-trivial background. Yes.
So when you say background, do you mean the underlying state is not the vacuum state, or what? Like
no, vacuum. The definition of vacuum is that it's just the minimum energy state. So that's in a quantum theory. That's always the definition of vacuum.
Right.
Now, by here I just mean that I want to understand the fluctuation about some non-trivial background. It may not be a vacuum of the whole theory, but you can even assume this to be vacuum. But for that, I'm not insisting on that, because you see I haven't written down any potential or anything and showing that this configuration leads to minimum energy.
How should I think about the background?
So that's what I'm telling you. So let's say you are in a lab. You can set up an electric field in the way you want. Right? You say that electric field is constant or some functional form, you set up. Then you can always ask the question that now if I change it slightly, so I do a small fluctuation about the average electric field I have set up, and then ask this fluctuation propagates with speed more than the speed of light or less. That you can always ask. Now here you see you are not even interested in the question whether the average or the background field you have set up minimizes some potential or something. That's not you are asking. You can always set up an electric or magnetic field in the way you want in a lab, and then ask about the speed of fluctuation about that background. That you can always ask, and you see that whatever be the background is, or the average value of the electric field, I'm saying average because since you are allowing for fluctuation, it's the background means just the average value of the field. The fluctuation should never propagate with velocity more than c, because as you know, nothing can propagate with velocity more than c, so fluctuation should not. And if it does, then you can always go to a frame and then the ordering can be interchanged.
I mean, I would still understand it like, so the vacuum that we usually talk about, like you said, it's like the absence of any field is the vacuum, right? Or the
no, not absence of any fields. Consider a scalar field. You know, when we say the vacuum expectation value of the scalar field, what do I mean? That say for we say that Higgs field has a vacuum expectation value. So when Higgs has a value which is typically 240 GeV or something, that minimizes the potential. So in the vacuum, it's not that the field the value of the field is 0. It's the value of the field which minimizes the potential in that case. So in quantum theory, vacuum doesn't mean nothing. This is true even in quantum mechanics. You know that even in simple harmonic oscillator, the vacuum state has non-zero energy, right? This is the 0 point energy, right? So in quantum mechanics, vacuum doesn't mean nothing, because it's just one state in the Hilbert space, And this is the minimum energy state in the Hilbert space. That is the definition of vacuum, and that's why the word vacuum can be, a bit, sometimes people get confused about this, but you always think of quantum mechanics which has a Hilbert space, right? And what is the vacuum state? It's just the lowest energy state in the Hilbert space. That lowest energy, it doesn't have to be 0, it can be anything. Okay, so now you consider fluctuation, very small fluctuations about that non-trivial background. Now, by the way, in this case, you see there is no potential because I have assumed that it's symmetry, so it's always there is a derivative, so that's why there is no potential. So they all have the same energy. I mean, this derivative equal to constant, it really doesn't matter. But this is the background I'm considering, and then you can have a linearized equation of motion, and this is what it would look like. I mean, this is super simple. That's why I'm showing this example. I mean, you can just do it in half an hour, and then you can write down a dispersion relation for the wave mode, and this is what you get. And from this you can compute what the phase velocity is. In this case, since there is no mass, the phase velocity, group velocity, they're all the same. So this is omega by k, and what you see is very interesting, that you get a 1 minus something which modulo this constant k, which we wanted to learn about, is positive definite, because there's lambda to the power 4 mods k square and c dot k square. So now if you demand that this quantity must be less than 1, then k must be greater than 0. Yes. What is stopping? Del square? What is stopping? Sorry. Second, no, you can write many different terms. Now I'm just giving you one example, that if you write such term, then whether you can derive some constraint. Now you see that from these you get this very surprising constraint, that unless k greater than 0, the theory secretly allows you to have propagation of information with speed more than the speed of light, and this gives you a constraint that k must be greater than 0. Now this is very surprising. This is very surprising because you started from a Lagrangian which was Lorentz invariant. So you might think, or you might have thought that no matter what you do, the relativistic causality will always be satisfied independent of the value of k or the sign of k, but you see that this is not true. Now you can do the same exercise for Euler-Heisenberg. It's just slightly more involved because there are this mu indices, but essentially the same. And this also shows that the C1, you can do the same exercise for the other operator C2, that both actually have to be greater than 0. Both C1 has to be greater than 0 and C2 has to be greater than 0 without doing any UV completion. You see here in this analysis, I'm not even assuming that the Euler-Heisenberg term was generated from QED, from electron loops. I'm not assuming anything. I'm just assuming that this theory should not allow us to have speed of fluctuation, speed of small fluctuations about non-trivial backgrounds to be more than 1. Of course, we know what C1 and C2 are, and I showed that C1 is some 1 by 70 and so on. They are positive. They must be, because otherwise they would be inconsistent with relativistic causality. Okay, so now I'll be gradually be more and more technical. Now we'll see that I'll derive, or I'll show how one can derive the same constraints in a more involved and in some sense also a more powerful way, using the known properties of S matrix in a Lorentz invariant theory. And here you don't even have to consider non-trivial backgrounds and so on. So yeah, just a minute. So if you did not like the fact that you are turning on non-trivial background, you can even run this analysis, and you will see that the same conclusion can be reached from this analysis, although in a more involved way. Yes.
Why is it necessary that this disturbance has to be something physical?
So because you know that for wave modes, I mean you use okay. So you could have asked that why I am talking about phase velocity. If probably this is what you are asking, if I understand correctly, because phase velocity in general is not the speed of propagation of information.
I mean, maybe that's how it is correctly interpreted, but I just mean that you're using the concept of some physical object cannot be faster than the speed of light. I want to see that this thing that you're using is actually a physical object.
Yeah, that's why in fact in response to the other question, I said that you can exactly set up this in the lab. You can, so for the electromagnetic case, you can set up an electric field which satisfies the non-trivial background I mentioned, and then just slightly fluctuate it and see what speed it propagates. So this is exactly what you can set up in the lab.
So like I have the electric field and I.
In fact, okay, just to so you see that this always I do. So if you find it even difficult to think about electric field, even for normal strings. And
Okay.
what is we fluctuate and ask what is the speed of propagation, right? You can do even for sound waves. For sound waves is also exactly the same. They are density waves, more easier to think about. So you have a density, you slightly fluctuate and ask what the speed of propagation, and given the fact that nature is secretly Lorentz invariant, that I'm always assuming, you don't want the fluctuation to propagate at velocities more than c, and that's why sound speed can never be more than the speed of c. If you're still confused, we can talk.
No, I got what you're saying is in the example that you put, in that example, what would be this fluctuations physical interpretation?
So in the electromagnetic
That
example is
partial phi. And
so there, of course, pi is a scalar field. So this is just to give you, an example of a field theory, and that's why I said for electromagnetism you can really set up this in a lab. 4 photon experiment has been done quite some time back. So now so we'll do this asymmetrics analysis. So first let me tell you what the ingredients are. So we'll be talking about 2-2-2 scattering. Yes. Okay. So phase velocity, now in the simple example of electromagnetism and the pion, you see that this case is here there's no mass for the field, so that's why phase velocity is the same as group velocity. There's only one scale, so that complicacy does not arise. However, is an important point that in general one has to be slightly careful, and then you can't just demand that phase velocity cannot have a value more than c. In fact, there are known examples where phase velocity can be more, and that is not inconsistent with causality. So in general, I'm just making the statement that in general phase velocity more than 1 is not inconsistent with causality, but in the simple examples it is inconsistent with causality because phase velocity is the same as group velocity. So now I'll be talking about 2-2-2 scattering. Just to simplify things, let's consider 2-2-2 scattering of scalars. This is simple, most of you have done. We'll assume Lorentz invariance. Of course, that is our the main assumption. And if it is Lorentz invariant, you know that for 2-2-2 scattering, it can be written in terms of the Mandelstam variables, STU. However, there is a relation between ST and U, S plus T plus U equal to 4m square, where I am assuming the mass of all the particles to be m. So that's why the independent variables are S and T. And we'll be interested in the forward limit, and you can say that the forward limit is equivalent to setting t equal to 0. So finally, the amplitude is just a function of Mandelstam variable S. These are just definitions. Then there's something called crossing symmetry. You know, these are not assumptions. These just follow from the structure. This tells you that the S channel and U channel processes, they're related by crossing. So for identical scalars, it turns out that this function AS is symmetric around S equal to 2m square. I'll use this fact later on. So I mean, they're just some with some algebraic manipulations you can derive them. Then there is one very non-trivial thing which of course requires a detailed proof, but it has been proved quite some time back in the literature, that the causality, which is a statement of commutator vanishing outside the light cone, which is again following from Lorentz invariance, tells you that this quantity ms at fixed t, I'll take t equal to 0, is analytic except some poles and branch cuts. This is known. This is called analyticity of the S matrix. And unitarity, you all know. I'll use optical theorem as the statement of unitarity, which you have learned even in quantum mechanics. So this is even true without Lorentz invariance. Even in non-relativistic quantum mechanics, that is true. And then finally, I'll also assume that the function m as a function of S is bounded by S log square S. This is called Freusser-Martin bound. This has been also proved in a Lorentz invariant unitary theory. There's a one catch with a mass gap, but I think let's not worry about that technicality for now. Okay, so these are the things, but you see the main point here is that you have Lorentz invariance. Once you have Lorentz invariance, more or less everything follows. Okay, now so you have a function. Now it's complex analysis, and you will see the power of complex analysis and why one should learn complex analysis. So now we have a function A or M, the amplitude as a function of S, and we think of, we analytically continue this function in the whole S plane. This function, as I said, there will be some branch cuts. It turns out that if the masses are m, this branch cut starts from 4m square, and then there are some poles. So now let's consider this integral, which I wrote down in the second line. A by S minus m square. M is some arbitrary point in the plane. So let's just consider this integral. You'll see why this is useful. If you consider this integral, since you see that there's a branch cut, and this starts from in the S, it starts from 4m square to 0, and because of the crossing and U channel, it goes from minus infinity to 0. Sorry, 4m square to infinity and minus infinity to 0. These details, if you can't exactly follow, you can just sit down and learn it very easily. And this tells you that this integral is the same as the value of the integral, value of the function, or the discontinuity of the function across the branch cut. This is just from complex analysis, assuming that the contribution from the arc at S equal to infinity vanishes, and which will vanish because of the Freusser result. This A is bounded by S log square S. So, and since we are considering A by S cube, so at large S, this will vanish. So that's why you don't have any contribution from the arc, you have only contribution from the discontinuity across the branch cut. Okay, once you have that, so that is the right hand side of the last equation. And by Cauchy's theorem, you know that it's also the integral can also be computed in terms of residues at the poles. So that's what I've written in the left hand side. So there's a pole at s equal to m square, and then there could be other poles at if there is an exchange diagram, there will be poles at m square because of propagators and 3m square and so on. Okay, so now the discontinuity of the amplitude, or which is related to this is the imaginary part of amplitude. This is complex analysis, and now you all know optical theorem from quantum mechanics. This tells you that the imaginary part of the amplitude is s times sigma s. This you know that the imaginary part of the amplitude is related to forward scattering. This is what you learn in your quantum mechanics class, and I have already assumed forward scattering. That's why I said t equal to 0. So once you do that, you'll see that the right hand side of this equation becomes s sigma s by s minus m square. I mean, you can do some little bit of algebra. So forget about the correction terms. You see that what you get is ds s by s cube, which is 1 by s square times sigma s. Sigma s is positive because it's a cross section, a square is positive, and that's why this quantity is positive. And on the left hand side, what you get is you can just write completely generally the amplitude in powers of a square. On the left hand side, you pick up C1, C4 and C4 prime. Forget about C4 prime. Let's see why C1, because C1 is defined as the part of the amplitude which goes as a square, and we are interested in the residue at s is equal to m square, so that's why you picks up this coefficient. So you get C1. C4 prime you get if you consider exchange diagram. But now this looks involved, but now you can apply this to this Lagrangian. Again the Payen Lagrangian, what you do, you compute 2 to 2 scattering, you extract the a square piece. If you extract the a square piece, and you can guess why this del pi to the power 4 will give you a square, because del has, this has 4 derivatives, each derivative gives energy, so it's energy to the power 4, which is a square. So it gives you a square, and so the C1 in this example exactly becomes k, and what you get is k greater than 0. So from these also you reproduce again the positivity of k, and you can actually do the same exercise for Euler-Heisenberg, and you will see that you will again get the same positivity C1 greater than 0 and C2 greater than 0 using the S matrix positivity. This is fast reassuring, because two completely general techniques, completely different techniques give you exactly the same bound. And on the other hand, it's also surprising, at least to some extent, because the previous analysis had nothing quantum in it. Because we're writing down a Lagrangian, we are solving, we're writing down equation of motion. This is completely classical field theory, and we are asking about subluminality, or demanding subluminality of fluctuations about non-trivial background. So there was no quantum mechanics involved. Here there is a lot of quantum mechanics. First we define S matrix, then we understand what the analytic behavior of the amplitude is. There are poles, branch cuts. Then also we have, we crucially need Froiser's bound, this polynomial boundedness, because otherwise the contribution from the arc would not vanish and you can't do anything here. So you actually need a lot of things here. So naively, the previous method, which I would call as classical causality, because there is no quantum mechanics in it, naively is more powerful because it assumes less. And this one, amplitude's positivity, it's rigorous, but it has more assumptions inbuilt. So that's why it's also a bit, naively you could have thought that this will give you better constraint because you are assuming more, but it turns out that they exactly give the same thing. Now but you see, these are all in relatively simple theories. In electromagnetism, in a Payan Lagrangian, which is also a simple case. But now you can ask whether this positivity of some coefficients of operators, this continues to hold in a more involved examples of non-abelian gauge theories. That's what we'll do in the last maybe 10 minutes or so. So in non-abelian gauge theories, you see, is more complicated. The first two operators exactly look like the ones we had for Euler-Heisenberg if you replace G by F. But since this has color indices, there you can write down many more operators. On the other hand, you can also write down operators which involve only 3 field strengths. This you couldn't do for the Euler-Heisenberg, because this is abelian, and you can show that if you replace G by F, because there is no this ABC indices, this will be identically 0. So in non-abelian, you can write down dimension 6 operators, these 2, and then also dimension 8 operators, but more than 2. Okay. Now for the dimension 8 operators, like the way I said, that you can have a contact diagram in 2 to 2 scattering, and this will go as a square. For the dimension 6, you will have an exchange diagram, and each vertex will have 3 derivatives, and if you count the number of derivatives, and then there is also propagator, which gives you 1 by p square, you will see that this also goes as a square. So what you will get if you compute the a square piece of the amplitude gluon going to gluon, you will get terms which involve the coefficient of dimension 6 square, because there are 2 insertion of the vertices, and then dimension 8. So let's call the coefficient of dimension 6 as C6 and the coefficient of dimension 8 as C8. So it would be of the form C6 square plus or minus C8. So if you do the details, don't try to read the whole table, you will get constraints which are like C8. Okay, this 3 is the index for the particular operator. Forget about the superscript 3. C8, some Wilson coefficient C8 is not greater than 0, but in fact greater than some numerical factor times C6 square. Because in the amplitude you had contribution from exchange, which was C6 square, you had 2 vertices, that's why C6 square, and then also from a contact diagram, which is C8. So you see that of course you don't have to see the details of how the constraints are, but you see that these are all the different constraints you are getting from the asymmetric positivity, and none of which you could even guess if you guessed just based on gauge, at least naive gauge symmetry and Lorentz invariance, because the operators we wrote down were anyway gauge invariant and Lorentz invariant. In fact, you see that there is something very interesting happening here. The C6 is the coefficient of, let's say, one of the dimension 6 operator, let's say QG31, and C8 one of the dimension 8. They are individually gauge invariant. So you don't expect any relation between the coefficients of one operator to another operator, because they are individually gauge invariant. Coefficients are arbitrary. So you could never guess that the consistency of the theory, by consistency I mean that the fact that the theory in the UV must be Lorentz invariant, that tells you that the coefficient C8 must be more than some numerical factor times C6 square. Now this, by no EFT analysis, power counting, symmetries, there is no way you could have guessed anything like this. So that's why you see that this is so powerful, and also the volume of constraints you get on this coefficient already shows that these coefficients are far from free. they are quite strongly constrained. Now you can ask whether in this non-trivial example of gluons you can reproduce all of them using also the classical causality, this fact that fluctuations should not propagate with speed more than c. That turns out to be a bit complicated exercise, and I really don't have time to go through it, but it turns out that you can do that exercise, and that becomes complicated because also of this issue of phase velocity and groove velocity, because for non-abelian examples you get in the dispersion relation you get terms which are mass like, so you have to be more careful, but nevertheless you can do the analysis and you can show that all these constraints, in fact all these constraints, considering different colors and different combinations of polarizations, can be reproduced by just the classical causality analysis. This is very interesting because this is a very non-trivial example. This theory is extremely nonlinear because this is non-abelian gauge theory. But even in this case, just the classical causality argument does reproduce everything you obtain by the S matrix positivity argument. But now you can ask whether, then you are also slightly puzzled because these two are completely different, because one is just a classical statement and another relies on a lot of quantum mechanics, optical theorem, this and that. So whether one can find an example where they give different bounds. And in fact it turns out that that can be the case, and there's the last thing I'll discuss and stop in 2-3 minutes. So here is an example of a theory which is not Lorentz invariant. This is a non-relativistic example. This is an example where Lorentz invariance is spontaneously broken. For those who do cosmology, they might know that the first line is motivated by something called an EFT of inflation, but that's not so important. You have this non-relativistic Lagrangian. You can do the amplitude analysis, which in this case is a bit tricky. So the analysis should be taken with a pinch of salt. But nevertheless, you get some bounds that C4, the coefficient C4 greater than 2C3 square. Now, running the classical causality argument is very simple, because you just get the equation of motion, compute the dispersion relation, and demand that the speed must be less than 1. You can do that, and you will see that that gives you C3 equal to 0, that C3 must be 0, because you get V phase square is 1 minus something proportional to this alpha, which is C3 times alpha, where alpha is some arbitrary number. If you demand that this can't be more than 1, then there's only one possibility, the C3 equal to 0, and it also gives C4 greater than equal to 0. Now, while this is consistent with what you get here, if you put C3 equal to 0, but this is weaker because this is not telling you C3 greater than 0, sorry, C3 equal to 0. So this is one example where you see that the classical causality in fact reproduces stronger bound than S-metric positivity, which is also naively very surprising, because in the other analysis, which is S-metric positivity, you are actually putting in lot more information, so you should get out also more results from it, but that's not happening. So a lot more work is necessary to understand this better, but this is just to give you one example to show that don't assume that these two will necessarily produce the same constraints. No. So that's why I said that here I'm assuming that this is a theory where Lorentz invariance is spontaneously broken. It's not explicitly broken. So the theory secretly is still Lorentz invariant, and that's why you demand that nothing should propagate with the velocity of light. So it's almost like this, in the real world we don't really see Lorentz invariance, right? But this Lorentz invariance is not, we know that secretly nature is Lorentz invariant, and that is why even in this naively not Lorentz invariant world, nothing can propagate with velocity more than c. So this is different from explicitly broken Lorentz invariance. So this is so that's why I said that here this is a case where Lorentz invariance is spontaneously broken. So that's why you will not see this. So the physics will not look covariant. So if you are in one frame, if you go to other frame, the physics will look completely different. But if you can stick to one frame, but in that frame you can still demand that no information should propagate with velocity more than c. And this is this is what we always do, right? So we in Newtonian mechanics is not Lorentz covariant. You go to a different frame, physics look completely different. But still it's true that in any frame, no information should propagate with velocity more than c. Okay, so yeah, I should really stop. So the take home is the following. So low energy effective field theories really play a central role in physics. So it's really of paramount importance to understand the space of allowed low energy EFTs in whatever ways possible. The question we asked is the following, that what is the space of low energy EFTs that admit the UV completion either through string theory, quantum gravity, or within field theory alone. In this talk I only talked about the last part. That means I only talked about quantum field theory in a non-dynamical flat background, and that fat black and that's why there's only Lorentz invariance. And here as I showed that you can ask these questions and you can try to rigorously answer and prove or answer some of these questions. Asymmetric positivity and classical causality tell us that the space of allowed coefficients is far from being free, and they are actually significantly constrained by positivity or classical causality. There have been a lot of recent progress in this direction. In fact, people have found out that these kind of ideas can give you even two-sided bounds. By two-sided, I mean, the bounds, at least in the initial examples, the bounds are one-sided, that's c greater than 0, right? But it turns out that you can even get bounds where the coupling is greater than 0 and then coupling also has to be less than something. So this kind of two-sided bounds or compact islands can be seen from some of these ideas. It turns out that many of these two-sided positivity bounds overlap with bounds derived from a program which is called the S-matrix bootstrap program, which uses the power of full unitarity, and by full unitarity I mean also going beyond the forward limit, because if you remember your quantum mechanics class, the way you derive the optical theorem, in the last step of the optical theorem you take the forward limit and you relate the imaginary part of the amplitude to cross section. But even in the previous step you have a full statement of unitarity. It just follows from in the S matrix language that S dagger S has to be 1. So they use the full power of unitarity for each partial waves. So then for each this you also do in optical theorem, you write down the amplitude in partial wave and then you proceed. So that's what they use. And more interestingly and very recently, people have found out that even ideas like quantum entanglement and violation or non-violation of Bell inequalities can be incorporated in this program and can give similar bounds which people have derived from this positivity program. Now this is extremely interesting because you see that here the entanglement is not a statement about spatial relativity, it's just a quantum mechanical thing. So if you can derive the same bounds from just quantum entanglement related ideas, then naively it would mean that it doesn't even rely on spatial relativity, which for my talk was the central theme. We are always using spatial relativity and relativistic causality to get the bounds. So that's why this is a very recent development. So that's also very interesting. And then there are additional questions about how to generalize these two theories where Lorentz invariance is spontaneously broken. As I told you, that the amplitude S-matrix positivity analysis for spontaneously broken Lorentz invariant theories are slightly tricky, and that's why I said this result has to be taken with a pinch of salt. So in that direction also there are unanswered questions, and that direction is important because whole condensed matter physics falls in that category where we don't really see Lorentz invariance explicitly, it's spontaneously broken. And lastly, these ideas have been used also to constrain EFTs of gravity, where for various reasons things are more complicated, but there have been a lot of progress in that directions too. So I'll end here just by thanking my students who have taught me many of these things while working in those two papers, my master's and PhD students. And finally, I again thank you for allowing me to share my excitement of doing research in this area and making me part of the celebration of the 60th Foundation Day of this institute. Thank you.
Thanks, Diptimoy, for this fascinating talk. So, questions?
So this example that you kept coming back to, partial pi square plus partial pi 4 to the 4. So in that, if you try to calculate the Hamiltonian, from there you get that if k is negative, the Hamiltonian can go to negative values, right?
K is negative, Hamiltonian, so why?
So Hamiltonian is just the Lagrangian in this case, there's no potential. So if k is negative, the partial 4 term can beat the...
Okay, so you see that this is, this is a good question. So, let me...
From that itself, maybe you can say that this theory is unphysical.
I'll tell you. So, just for... so this is the Lagrangian. Now you see that first I say that this is an EFT, and this EFT only makes sense when the del by lambda is very small. So this is an expansion in del by lambda. So you should never take del by lambda to be very large. And once you have del by lambda to be much smaller than 1, you will actually never hit that regime which you are talking about. So in the EFT regime, and that's very important because at every step of the calculation I have to make sure that my EFT is valid, because otherwise you can add the del pi to the power 100 and they'll be even more relevant than this term, right? So that's why here this probably I did not mention this clearly. So I'm writing an EFT. This is an expansion in del by lambda, and for the EFT consistency I'll always assume that del by lambda is much less than 1.
So what should be the interpretation of like having this positivity constraint of this matrix and the classical causality are giving same bound? How can we interpret that?
You see okay, you see.
I mean that is strange. Like the two
No,
things.
it's not strange. I won't say it's strange. In some way, it's expected because you see both relies on Lorentz invariance. Because both are relying on Lorentz invariance. Okay, the in between the calculation steps are different, but they'll produce finally the same result. So in that sense, they're not. It's not strange. However, you can ask what are the minimum set of assumptions you need to derive the positivity constraints. Then from the classical causality arguments, you will think that, oh, you don't need really quantum mechanics. It has not, the fact that you get some kind of positivity constraint has nothing to do with quantum mechanics, because I run a completely classical wave analysis. So what it is a completely classical wave analysis, I get the positivity. And however, in the S matrix positivity analysis, I'm putting in a lot more. I'm doing quantum mechanics, then optical theorem, then unitarity of the S matrix, a lot of things. But that's why you might naively expect that since you're putting in more, you'll also get out more. But if the true constraints, you see the true constraints is just this, then that can't produce more constraint than this. You can use more and more, you can put in more and more, but it's the fact that you are getting the same thing is nothing inconsistent. You might want to understand it, that why putting in more is not giving me more, but it's not inconsistent. So that's why I said that it's interesting that just the classical causality gives us the same set of constraints, even in a non-trivial example of the gluons. And one might want to understand it more, but there is nothing obviously wrong in this.
Actually, I had a similar question to Anu. So, so naively, I would expect that the tree-level scattering amplitude gives the same result as the classical causality argument, isn't it? Like naively, I would assume that the tree-level scattering amplitude will give the same result as only at loop level will get
okay, so you are probably thinking that tree level is equivalent to classical.
Not exactly, but like...
No, but you see that is not really, I mean, in this here, really, I mean, the classical, I mean, this is often said, but you see that this one has to qualify this with this statement properly. You see that what I am doing a completely classical wave analysis. Now, classical wave is not equivalent to a tree level thing.
Yeah. Not exactly. Yeah.
Is not. So, in fact, you can even think of the classical results in the classical thing as a resummation of in many loops. So it's not that whatever you get from a tree level thing is something which you should always expect to get from a classical wave analysis. And in any case, you see the tree level analysis also here, I mean, you can do a loop also, but that uses a lot more. That uses quantum mechanics, unitarity, Froissart's bound, a lot of things.
But also, also you said like we are not getting extra things from there, but
no, we are not getting extra thing only in the examples I considered. In fact, that's why in the last example, you saw that we are actually getting extra, but in the classical analysis. That's interesting, but that's why I said that the bounds you get from amplitude analysis that you should take with a pinch of salt, because there, since Lorentz invariance is spontaneously broken, some of the assumptions of the amplitudes positivity analysis actually are not completely valid. So in that derivation, there's some assumptions. But in any case, this is one example which shows that it's not necessary that both will produce the same bounds.
There were also some extra terms in that expansion, so like C1 plus C4 plus C4 prime, but you only talked like what were,
No,
doesn't they give us extra information about
which
these-
expansion?
just before that, yeah, here so what, so
No, these are just various contribution to a square piece.
oh, okay.
Various contribution to a square piece, you know. So it's,
okay.
it's just because, you know, here a square is also getting you're getting contribution also from the exchange diagram. You see, in the pi and Lagrangian there was no exchange diagram.
Yeah.
Right? There was no 3 pi and vertex, so that's why this did not. This wasn't there.
Thanks.
So the analysis you did comparing this to approaches to constrain your theories, is it very much dependent on the theories you chose, or can you do a more general kind of proof that these two
no,
approaches?
you see the thing, you have to take a theory and do the analysis, because you see, in different theories the dispersion relations will be different. It really depends on the structure of the equation of motion, what terms are there, and so on. Say, for example, in the non-abelian case, you see it's complicated because when you write down the equation of motion, you see there is this del square, this H is the field, del square field, and on the right hand side you see that there is a linear term in the field. So you see, whenever you have a mass term, whenever you have a m square phi square, you do equation of motion, you have linear term in the field in the equation of motion. So, and this term will tell you that the phase velocity is not the good thing to consider when you are talking about causality. So you have to check, to be safe, you have to check whether choosing various colors and polarization you can make these mass time terms vanish and get some constraints. It turned out that this was true, and that's why you could reproduce all the constraints. So the whole analysis is theory dependent. So you can't, I mean, you can't say anything, you can't prove some theorem saying that this will give necessarily the same result as the other analysis. At least I can't think of any way of proving such a theorem.
But
there are some gravity as well as non-abelian relations, relations between scattering processions and there are recurrence relations between scattering processions and different orders.
No, that is, but that is in the context. So this is this on-cell method, but I don't know whether that will help us anyway. So that is this like the BCFW relations, which just tell you how the on-cell scattering, let's say of 4-point scattering, amplitude is related to 3-point, the recursion relations. But here we're not doing anything like that. No, here, you know, I mean, here is, I mean, here you see, this is not a question about how different endpoint functions are related. It's a question about the a square piece of the amplitude and how that is constrained.
so what do you expect though? Do you think this is true for other theories which are Lorentz invariant? Or you have to just check case by case?
I don't know of a Lorentz invariant example where these two analyses produce different results. However, I should tell you one thing. If we have fermionic theories, there this S-matrix positivity is the only thing to do, because turning on a fermionic background, I mean, I don't know what it means by turning on a fermionic background. I mean, it really, I can't think of turning on a fermionic background and do some wave analysis. So for fermionic theories, you see this classical causality thing, it just does not work. At least I don't know how to make it work. I mean, I don't know how to even physically think about it. So in that case, I think the S-matrix the analysis is the only thing. If you have you can then think of a bilinear condensate, its equation also is more complicated. So in simple fermionic theories, you know, I don't know what now what one means by turning on a fermionic background or considering fluctuations of propagation.
That-
So it's
the
physically
fields-
at least it's,
physically the fields
it doesn't make sense.
Yeah, but any further questions? No? Okay. So we can discuss further outside in the high tea. And thanks Diptimoy again for coming and giving such nice talk to all of us and patiently explaining all the questions. And thanks a lot.